All right, guys. Do you remember where we stopped? It's this very confusing thing about the exponential function. So very briefly, we verified that we can understand what it is by imagining that we are dealing with an infinite polynomial. Yes? So e to the x happened to be the same as 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, and so on. Remember the idea that led us to this problem, right? We were investigating derivatives of exponentials. We were stuck at a limit that we could not figure out directly. And then we realized that we are interested in a differential equation. And this differential equation is where we are trying to find the derivative of a function to equal itself. And so that it's not the constant zero function, we wanted the function at 0 to be equal to 1 because all exponentials evaluated at 0 equal to 1. That was our goal. If you learned a little bit of combinatorics, and if not, you can stay with me, we can discuss it, or you can read my notes for the probability class. With a little bit of combinatorics, you have this optional section. You understand that exponential function can be thought of as, well, as this infinite series, it's called, as an infinite polynomial. And then we can verify indeed that you have all the exponential properties. We have this addition to multiplication rule, okay? But when you think about it, you most likely understand what it means to, let's say, take 2 to the power of 3 and 2 to the power of 4, but you might not know what it means to take 2 to the power of root 7, okay? So this addition to multiplication rule can actually be verified rather directly through the use of binomial theorem, okay, where you multiply it. And that's what I explained in this optional section. I cannot devote too much time in this course. Okay, so this is very easy to understand. All you need is just to know a little bit of combinatorics. So this is truly how we define, and then we show that it behaves like an exponential function in all instances where we understand its behavior. And today, I hope you have taken a deep breath, is the other part of this function, is that we need to also understand exponential limits. Okay, and then we talked about, we already mentioned this problem, right? So we have this glass full of tea and another glass full of rum, and we sample one molecule from this glass and then replace it with a molecule from the second glass. And we continue sampling until no molecules are left. And the question is, what's the probability that the last molecule removed happens to be T? Going through the process, we came to this limit. Remember, limit as n goes to infinity of 1 minus 1 over n to the power of n. And we then stated without any understanding as of yet that this limit has to be e to the minus 1. So take a deep breath. We are going to try to understand this limit. Okay, guys, so here is how that's supposed to work. If the derivative of a function is the function and the function at 0 is 1, then we can try to understand what this function is like by appealing to the definition. Limit as h goes to 0, f of x plus h minus f of x over h. And that's the definition of the derivative. It equals to the function itself. What does it mean? It's just a fraction. That means if h is really small, if this number is the perturbation of x is very small, essentially I can drop the limit. So essentially, if h is small, we have f of x plus h minus f of x over h is roughly the function itself. Before I continue, guys, are you with me? Confirm, since I only see a few of your faces. By the way, hello, James. Sorry, I haven't answered your questions just yet. I was extremely busy. I actually will show you, if you're interested, in my phone what happened this weekend.
No, it's no problem. I was just practicing problems, but I'm gonna stay after class anyway. So sure.
I'm glad. So guys, if you have the strength in you, stay with me. We can understand everything. So much to cover and so much to understand. So good. Where were we? Right. So you all understand. Confirm, please. Write yes or ask me some questions if you are stuck. Do you understand why this statement can be replaced by this weak equality statement, but I drop the limit?
Why do you drop the limit?
Because I'm going to actually create a recursive formula. I'm going to, you see, look what I'm going to do. I'm going to walk back to 0. The only place where I know anything about this function is at 0. Again, I'm looking at it, you know, we already verified actually how to calculate it at any x, but I'm actually trying to show you how this limit arises. 1 minus 1 over n to the power of n. This type of limit is very frequent. You see it all the time in mathematics. And I want to show you how that limit arises, okay? And we're again trying to solve this differential equation yet another way, okay? We have the derivative of a function is equal to the function, and the function at 0 equals to 1. Yes? You are with me, guys, right? I think I mentioned at least one simple reason why you care about functions whose derivative is equal to itself, right? It's with this poltergeist explanation. You want to search for the invariant. If it doesn't change, then under differentiation, then it's something very specific, very important in revealing about differentiation as an operation. Good. So then once we are at this line, we realize that what I want to somehow walk to 0. At 0, I know the value is 1. Anywhere else, I mean, you know, if I restarted my problem from scratch, I mean, I already showed you the summation. You already know how to evaluate it at other places. Yes? Good. So you see, guys, I can drop the limit because then it's just a fraction and I can make manipulations. You will see in a moment, okay, guys? So just bear with me. It's a bit difficult what I'm saying, but hopefully you will be able to follow. So I will later present it in other ways of doing the same thing. So in evaluating this limit, I'm going to drop this limit and say, well, it's not equal, but kind of equal if h is really small, okay? And then I'm able to just to move things across this like equal sign. So I multiply everything by h, and I have f of x plus h minus fx is approximately h times f of x. Yes? Good. Wonderful. Wonderful. I hope, guys, you can tell me if you're stuck. Again, tell me. I will try to re-explain. So what happens here? So then I move the minus f of x across the equal sign, and I get that f of x plus h is approximately f of x plus h f of x. And then I can factor f of x out. So 1 plus h times f of x is approximately equal to f of x plus h. What do I see in words? Look at it. There is no x or h that I'm seeing. I just see the following. The function evaluated at a number is equal to 1 plus some small step. The function evaluated at the same number minus that step. So that's called recursion. In other words, in order to evaluate this function at this number, I defer the calculation through this procedure by moving a step back. Are you with me? So instead of saying, don't calculate at this number, actually calculate the function at this number and walk one step back. And then I rewrite it in symbols. Here the meaning is different, right? X just refers to a number, the input, right? That means that the function evaluated at a number is roughly equal to 1 plus a step, the function evaluated at the number minus the step. Now this I need you to be understanding. Do you get how I obtained this formula? I just played with my definition of derivative formula and I get this recursion, okay? The goal to keep in mind is that I'm going to walk from x by tiny steps all the way to 0, because at 0 the function equals to 1. You understand? That's how recursion works. So if you don't know the calculation at the 100th step, you walk back to the 99th step. You don't know it, you walk to the 98th step. And you continue walking until you get to the initial place where you actually know how to calculate. In this case, it's at 0. Okay? So far, guys, are you comprehending? It's kind of a lot of information and difficult. I remember my best students, when I explained that, they had trouble understanding this part. So again, I encourage you not to look at the symbols, but to look at the meaning, right? X is just, what is it? It's just a number, right? What we obtain here, x plus h is just a number. Here the meaning of x has switched. So I'm just saying, this function satisfies this relationship. The function evaluated at a number is 1 plus a small step times the function evaluated at the number minus the small step. Just walk back, okay? So here is what I will do. I will take the interval from 0 to x, and I will divide it into many tiny steps. I divide it into n steps, where n is huge, maybe million steps. Imagine that there are million of dashed lines between 0 and x, and dividing this into a million, it will be less than a micrometer in length. Micrometer is, you will not see it, you understand? You would not see the difference between dashes. It would look to you like a solid line. You with me? This is far less than a meter, and therefore if I divide it into million steps, it will be much less than a micrometer. So you will not even see the distance of each step. So you're marking every tiny step, and then you would expect that you are not making too much error. So this is what happens. Look at it. So my step size, my h is x divided by n. That's my step size. Okay. So let's walk back by the step size. So the function at x is approximately 1 plus the step size multiplied by the function minus the step size. Evaluated at the point minus the step size. Are you with me? You see, that's the procedure that I obtained from the definition. You see, when you derive it, you should always close the book, don't look anywhere, look at this formula. Can you get to this line? Can you get through that line? If you carry this operation, you improve a little bit. Your reasoning is improving this way. So now I'm at this point. Look at it. I put a red line below it. So f evaluated at x minus x over n is the same as if I push in front of it 1 plus x over n, and I move one step back. So x minus 2 x over n. And I continue to walk back. How many times do I walk back? So this is 2 steps walked back. It's x minus 2 over x over n. 3 steps will be x minus 3 x over n. So I will walk n steps back, where n is a huge number, million or something. I'll make n larger and larger and larger to make less and less error. So x minus n over x over n will actually bring me to 0. You agree? So what I have is that f of x is approximately 1 plus x over n to the power of n, the function evaluated at 0, which is 1. And therefore the function is approximately 1 plus x over n to the power of n. And in the limit, I will get this. Limit of this function as n goes to infinity is going to be my function. And what was my function to begin with? There is only one solution to this equation, that's e to the x. Right? There is one solution that if at 0 I require it to be 1 and the derivative is equal to itself, there is only one solution. So that must be e to the x. There are of course many, if you're critically inclined, there are many things you might argue. How do I know the error does not accrue? But we ignore those doubts for now. We just kind of see, we play with it, and it looks like it must be true. Do you understand what we just verified? We now know very quickly that 1 plus x over n to the power of n when n goes to infinity is e to the x. Now quickly, if you understand, please carry out calculation A, B, C, and D. In other words, that's just an easy comprehension check of whether you get how this formula is supposed to work. Once you're ready, you type in the comments, okay? Okay, Mohammed, let's see what you're saying. It should not, guys, it must be a number, right? X means some number that, well, that you haven't specified, right? So none of those expressions can contain X. Yes, but from before, let's say, Muhammad, I don't understand how you got e to the power of X, because then I'll just do e to the 5 and take the numerator and put it over e for the other problems. Well, yes, that's true for A. Okay, guys, when what I said here, you should not rely on, maybe you feel that you understood, or maybe you feel that you didn't, but the way you test that you understood is that you think about it on your own without looking anywhere. Do you understand the idea? Do you understand what went on here? We reinterpreted the definition of the derivative, right? We're saying the derivative of e to the x is e to the x, and the value of the function at 0 is equal to 1. Yes? You're with me, guys? Right? So then what does it mean? It means I just call f of x e to the x here. Good, right? And then I understand what this part means. This is just the slope calculation. The slope is equal to the altitude of the graph, right? The slope at any point of the graph is the altitude of the graph. That's how this looks. And that means that if I approximate the slope, if h is not quite 0 but close to 0, I don't have to force the perfection. I just say h is a very small number, then this part is approximately this thing, right? In other words, in the limit is that this quotient here is becoming f of x. It's not f of x, but it's becoming f of x. It's morphing into it. And then that means that if you do not, that's what you do often, right? Thank you, Nassim. Very good. Very good, Nassim. So here, you see, we drop this limit. You understand why I drop the limit, guys, yes? What I'm having a conversation here. It's not like you're not plugging, you're not solving anything. What you should think is that you're having a conversation here. You're describing something, right? So then what this is saying is that this ratio is morphing into f of x. Drop the limit, and the ratio is close to f of x if, of course, you pushed h close enough to 0. And then you get this recursion formula, right? In other words, you have defined the function at a number to be 1 plus the step back that you take of the function at the number minus the step that you take. Okay, and then you just do this process, and you get this formula. I hope you understand how that worked. Okay, so then from doing this, we realize that limit as n goes to infinity of 1 plus x over n, whichever that x will be, is e to the x. It's this number. So then let's look at a. It's 1. Here x, that number is 5. So the first part of the question a is e to the 5. You see that? It's e to the 5. That's where we had the 5. Now over here in b, let me write it here, right? So what is this b thing? I can put here plus, and then it's minus 3 over here. So that is my x, right? So that's the thing that I put over e. Now 1 minus 1 over n to the power of n. Here the x is minus 1, so that's what I put here. The last question, 1 plus root of 2. So the x is root of 2, so I put it as the power of e. Okay? And how to calculate what this means, again, we already looked before that. Let's say, how do I calculate e to the minus 1? How does a calculator do that, for example? So e to the minus 1, remember that, right, guys? If not, it's just stay for after class, we can discuss that. What is this? This is 1 minus 1 plus minus 1 squared divided by 2 plus minus 1 cubed divided by 6 and onwards, right? So at some point you stop, you don't have to add forever, and then you don't get the exact value, but you get an approximation, right? The same thing with the limit. When we stop, we don't get the exact value, but we get an approximation. Good? Let's move on. I hope it helped, guys. Don't be shy, again, to ask me questions if you are lost. And I'm not going to go over that problem, but that we already mentioned one person was interested from the other semester, from the other class, that you see, we already saw that in this class we had 2 sets of birthdays, and that was very expected, right? With the amount of students I have here, I thought about 88% likely that at least a pair of people will have a common birthday, and that can be approximated with E. You see, if you look through this problem, you will see E there. I promise on your exam, I will give you a few interesting problems, right? There is one I'm giving for my probability students. And the question is, what's the likelihood that you are at this very moment breathing the air that was exhaled by Julius Caesar when he was killed? You know this question? You might have heard of it, yes? So, can you guess what this has to do with? I mean, how do I estimate that answer? It has to do with this rascal E, of course. So you see it all the time. Good? So let's move on to today's lecture notes. I hope this is interesting to you guys. And again, to some students, I already showed how to calculate roots, right? Without a calculator, how do you figure out, let's say, root of 2, root of 3, or general roots? How can you do that, okay? So hopefully that's something that it has actually something to do with, I thought of this, I remember this question because of the Chinese room experiment. Have you heard of that experiment? It's about artificial intelligence. Yeah, so if you're interested, guys, Chinese room experiment and everything else, and why do you care about roots? And it might be an extra credit for your exam if that's motivation. Okay, so stay and learn it. Let's move on to product and quotient rule. So let's see where we stand, guys. So I'm not expecting necessarily a right answer. I hope the answer is not going to be entirely wrong. Could you tell me or guess, or what do you imagine? Does your intuition tell you about the derivative of x squared times e to the x? What is that? Okay, ratio 2x times e to the x. That's okay. In the morning, my God, I lost it, right? I got so angry, but not because of the 2x e to the x, right? I got angry because of something else. Let's see what else. What do you say, guys? This, of course, we haven't covered, no problem, but just I wonder what sort of sense do you have? And Rafid, you're confirming, Rachel. By the way, guys, maybe add in another thing in your comments, right? What do you think the derivative is? And then tell me how confident you are of your answer. Would you have risked your life with this answer? I should make you more comfortable. Maybe you're right, right? Well, why does it, guys, here is this thing. Right or wrong? Is it right by accident or right by reasoning? Okay, James, 2x e to the x minus 1. James, okay. Okay. All right. So one thing that irritated me in the morning is this, of course, right? The derivative of e to the x. They said x e to the x minus 1. We just a moment ago, or we spent quite some time talking about this derivative, and we know the difference between e to the x and x to the e, let's say, right? So let me just open up, let me open up a new share. Here is the whiteboard, guys. There is a difference between 2 to the power of x versus x to the power of 2, right? Remember we mentioned that. We mentioned the difference, right? The difference is as glaring as, well, if this guy is your nice, happy fellow, then this guy is this thing. Remember that, it's completely reversed. Here, the base is changing, the power is fixed. Here, the base is fixed, power is changing. To confuse between those functions is terrible. Hello, Christian. Right? And remember what I mentioned, what it reminds me of when you confuse between those two functions. I think of this thing. And I don't think it is what you are imagining it is, right? It is not a pretty woman, no. It is a butt with eyes on it. You understand that you should not make this mistake, especially after we talked about what's the derivative of e to the x. We have all this explanation. I think, my God, we understand it. We're all together, right? And then I realized, no, nothing understood whatsoever. Nothing whatsoever. So you don't hammer it here? No, guys. Okay? So you should know them as intimately as if they were your friends. Let's continue. So this is the one mistake that irritated me, perhaps unduly. Maybe I should apologize in front of the morning students, but I was extremely upset because we spent what, 2 something extra lessons talking about it, and they don't stay after class, right? And then still this is not understood. The derivative of e to the x is e to the x. Good? And the derivative of x squared is 2x. We verified it. So then, is this solution? Does it look right? You look at it, right? I write 2x times e to the x, like many of you have. Am I correct? Am I correct, my friends? I told you, right? As I'm getting older, right? I think I'll just make a last lecture where I'll just teach you everything wrong, and I would see if would anybody notice that. It is absolutely, entirely, terribly incorrect. And why should you think it's incorrect? Well, maybe it makes sense or not. You know, how do you know that you should not be comfortable or not imagine this to be true? Is you go through the definition or you go through the concept all the time. You understand? It is not the purpose, I think, to teach you the product rule, because you memorize the formula. You can look it up. Why do you need to memorize it for, right? I want you to understand how the idea is recognized. So here is what we will do, right? We will do it in 2 ways. One way is the geometric approach. Okay, the geometric approach. Do you remember, guys, what I mentioned about differentiation? What does it mean for a curve to be differentiable? It means what? Hey, James, you disappeared. Well, how are you doing, James? Smooth curves, but what is a smooth curve, my friends? I say something like a curve is differentiable. What am I truly saying? When I said I saw a giraffe, right? What am I saying? Right? Could you describe a giraffe to me, right? Or what? Wonderful, Rachel. Right? Rachel sees that. Guys, you see, my question should not be so odd, right? Can you describe to someone what is a giraffe? So you would say, oh, I saw a big animal with very long neck that has an orange color, and it has black shard looking pattern, right? So it looks like a broken pottery on its back, right? You have some description. You can be good at describing it or not, but you do something. You know, it's not a blank. It's not emptiness. When a curve is differentiable, as one person in the comment noticed, let's see what about the others. It means that zoom in on any point on the curve and it starts to look like a straight line. You understand? You cannot tell it apart from a straight line. It's something so obvious to us, right? That's why people used to think that Earth is flat, because up close, definitely if it were a true sphere up close, it would look like a perfect plane. You would just imagine that you're walking on a plane. Yes? So the geometric approach is a function is differentiable. Yes, Rafid, you're funny. So you are zooming in on this curve. In other words, you're a small fly. You're landing on this curve that from a distance, here it is, right? From a distance, this curve does not look like a line, but zoom in at this location. And you see this long red line that I drew. The more you zoom in, those lines, this dashed line at the left and this dashed line at the right, they look like the edges of my screen. So I don't see anything. They look like my horizon. And all I see is this black curve. So still maybe that black curve doesn't look perfectly like a straight line, but then I can go closer to A. I'm flying closer to A, then the left and the right walls will be closer about A, and the entire thing will look more like a straight line. That's it. That's the property of differential curves. Does it make sense, guys? So let me see in the comments. Do you remember that? Does it make sense? Do you visualize this thing, or is it not clear? You're not just saying yes, right? So that I leave you alone, right? You understand this. You actually see zooming in on this curve, and you are seeing that it gets flat. Maybe you should program it or something, right? So you draw a curve, you zoom in, and when it's on the entire screen, you zoom in and zoom in and zoom in, and eventually it looks like one straight line. Good? So what does it mean in terms of calculations? So if I look at this function f of x and I zoom in, I see this line, which I like to call stunt double, okay? A stunt double because it will replace the action of the function f. The actual function f is like a prima donna. It's not easy to use it for calculations, let's say, right? But line is very simple. When I see an equation of a line, it's very, very few operations. I don't even have a square, right? I just have very few operations that I do there. I will give you an example below of what that means. So the word in Russian for stunt double is cascadeur, which, by the way, is also the French word and the German word. I used to imagine it's a Russian word because kaska is a helmet and дергать is to pull. So it sounded to me like, well, stunt double, you pull on a helmet, right? Sounds like what it's supposed to describe. So here is the idea. Look at this graph, guys. You see, this graph is representing possibly a complicated function. And using this function to calculate is difficult. So it's like a prima donna actor, right? So then, but locally, if I want calculation near the point A, I can instead use the linear approximation, the stand double function, which looks like this. The function evaluated at A, derivative of the function times x minus A. Let me show you how that is supposed to work in practice. So let's say that we want to approximate root of 9.01. Yes, using this linearization idea. So what does it look to you like? Well, it looks like 9.01 is really close to 9. Yes. So what I imagine doing is that I take the function f of x, which is root of x, and I will zoom in at this curve near 9 and see what line do I get. And use that line to carry out the calculation. So far you understand the philosophy, the idea here? Let's say, Joshua, wait, the red line goes with the red equation, and that's the stand double. The red line is the stand double, yes. The red line is the stand double. The word that they use is linear approximation. But the idea here is, you see, guys, look at it. Take this x, evaluate, you get this black value, this black point here, right? And that would be the value of the function at this x. And instead, what you do, you can take this x and plug it and get this value on this red line. And they are close. There is a distance between them. They're not the same, but they are close. And if my left and right walls are very close around A, I'm expecting the precision to improve. Yes? So far you understand, guys, the idea, right? So the idea is that it's not so easy to calculate root of 9.01, but perhaps if I replace it by a line, I will be able to carry out the calculation. But by which line? 9.01 is very close to 9. So I will carry out the approximation near 9. So let's actually remember, how do we take the derivative of root of x? We can do that this time by definition. So the derivative of the function is root z minus root x over z minus x. I can then represent z as root z squared and x as root x squared. And then I can factor the denominator. That's what I get when I factor the denominator. Yes, guys? So this is crossed out. And I have limit as z goes to x of 1 over root z plus root x. And then when I push z towards x, that's 1 over 2 root x. Good? That's the derivative at any point. So when I zoom in on my curve y equals root x, I will see that my line has this slope at the point I zoom in. So if I carry out the zooming in to the point 9 root 9, then what am I gonna see? I'm going to see this line, y minus root 9 or y minus 3 plus the slope is 1 over 2 root 9 times x minus 9. Are you with me, guys? You understand how that works? You look at me and then I think some of you are playing poker. Okay, what part do I lose you at, guys? Right, so here is the curve. Do you see that? This is the curve. I am going to zoom in at the point 9,3. 9,3. So this is this point, yes? This point has coordinates 9 root 9 or simply 9,3. Agreed? Why am I zooming in? Let me just verify, guys. Why am I zooming in at the point 9? Why am I interested in the coordinate x equal to 9 specifically? Remember what we had there? It's root of 9.01 that we're trying to estimate. Why 9? Okay. It's close to what we're looking for, and it's easy to calculate the tangent line, because remember the derivative, we just verified the derivative is 1/2 root of the x coordinate of the number we're zooming in at, right? If I zoom at, let's say 3, the slope will be 1/2 root 3, but root 3 is, you know, we don't yet know how to calculate it. If you stay after class, I'll show you how to calculate it as well. Okay, but let's say so at root of 9, it's pretty easy. Okay, calculating it at root of 9 is pretty easy. So I can calculate the exact slope over there, and 9 is close to 9.01. Okay, guys. So this is the equation of the tangent line. It's an equation of the tangent line. Y is equal to root of 9 plus 1/2 root 9 x minus 9. Do you remember how I calculate tangent line? It's y minus the y-intercept, x minus the x-intercept. Or in other words, we need 2 points, right? If we know a slope and we have 1 point, the equation is, do you remember that, guys? Yes? The equation is if I know slope is m and I have the point AB, then an equation of a line can be obtained by writing y minus b divided by x minus a, which is m. When I rewrite it, it becomes y equal to b plus m x minus a. And that's what I'm using here. Except b here is root of 9. And m is the tangent slope. Yes? So if I haven't lost you entirely, please write that you understand, so I know I can proceed. What about the rest of you? Guys, so don't just wait for my explanation, always think about it. It has to always be fresh in your mind. Always just go, when you're going home, when you're walking, just think about it. And it makes perfect sense then. And once it makes perfect sense, you don't forget it. Okay? So I zoom in and look at it. I even drew it here. I try to draw it, you know, as nice as I usually don't like to spend so much time drawing it, but here you can see here is this red line and here is the black curve. Do you see how close they appear? They look almost the same over this interval. And this interval is approximately, well, a distance of 1 unit. So 9.01 is really here. It's very close. We are not going to expect a huge difference. So I have this function, this stand double function, and instead of calculating root of 9.01, I'm using the stand double to carry out the calculation. Instead of plugging into the root function, I plug it into the linear stand double. Do you see it? 3 plus 1/6, 9.01 minus 9. And what I then get is 3 plus 1/6 times 0.01, which is 3.001 and 6 repeated. And by contrast, if you press root of 9.01 in your calculator, you get 3.00136. Look at it. So we have many digits correct by using the stand double. Good. As it happens, it's not a good tool, just the way I described it. You can use Newton's method or other procedures, but it's not a good tool by itself to estimate roots. Okay? It's not a good tool. It's not for that I introduced this idea. It's for a different observation that I introduced this idea. So if I take the derivative of f times g, I'm assuming that f and g are differentiable. This is what happens, guys, right? So x minus a, I will call dx for short, okay? So I'm interested to know what is going to be the line that I will see when I zoom in at the product f times g. Okay, when I zoom in at this product, what line will I see? And the way I think of it is this. If x is very close to the point A, then f of x can be replaced by its stand double, and G can be replaced by its stand double, by its cascadeur, by its linear approximation. Are you getting what I'm doing, guys? Instead of carrying the multiplication with those prima donna functions, I replace my actors by their stand doubles to carry out the dirty work. My goal, guys, do you remember my goal? My goal is to imagine what sort of line will I see and to figure out what slope will I see. So I carry out this multiplication, and I then can group the multiplication based on the powers of dx. Dx is, again, it's x minus a. So I have, I just FOIL the parentheses. I FOIL it. I just have f times g, f of a, ga, plus, look at it here, f prime times ga plus f times g prime. Do you see that? That will be, the sum will be containing dx. If you don't believe me, again, guys, I see, just again, write it out. Take this multiplication, make sure that you can arrive at this line. Come on, I want to see you do it. I see a few of you are staring at me, so do it. And those that I cannot see, do it still. Open your cameras, guys. I like to talk to you. I need to see your faces to know if you understand me. Are we done there, guys? Foiling. Just multiplying those parentheses. We're done? So you carried it through, guys? Yes or no? Almost.
Wait, Professor, can you
Yeah.
so wait, I'm still so all right, so the whole process with the root of 9.01, right? So we have to find the number that's closest in that area that makes a straight line, which is 9, right?
Uh-huh.
And after we go through that process, right?
Do you see where we found 9? We could have zoomed at 9.01. It's just if we zoomed at 9.01, we don't know, we cannot calculate the slope exactly, because then on the denominator we will have root of 9.01, right? We don't gain any advantage from that procedure. because
Okay.
the slope itself will already contain the solution to root of 9.01. So then I use this idea. Okay, 9.01 is really close to 9. It's not hard to calculate both this function and its derivative at 9. Yes, and then therefore it's not hard to establish what is the equation of the line that goes through 9, 3. Right, this is that equation. Here it is. It is simply 3 plus 1 over 6 x minus 9. And this equation, look at it. This equation is not the same as the curve. You can see that as I move away from 9, there is bigger and bigger difference between the line and the actual curve. So let's say if I were to use this line to estimate what's root of 5 is, it might not be good. You see, there is a gap here. Or
Yeah.
even worse, if I try to estimate what's root of 0.9, somewhere over here, there's going to be a big gap. But there is not a big gap over this blue interval. You understand?
Yes.
And that means that locally, right, for this stunt, for calculating roots in this blue region, this line segment works pretty well. So I can use this red line segment to carry out calculations for this region. For a different region, I will need to select a different line segment. That's the
Okay.
idea, right? So when I zoom in locally, but this is not why I like linear approximation, not really to approximate the function, but really to understand something about that function. I can understand properties of product rule is what I'm trying to understand currently, and I'm trying to show how that would work, okay? So again, guys, the idea is this, all right? So the function f and g are differentiable, which means that if I zoom in on the graphs of f and on the graph of g, I will see at some point a, I will see this equation of a line, you see? This will be the stand double. So it doesn't matter if I calculate it or not. That's not my point. I'm just trying to figure out the relationships between the derivatives of f and the derivatives of g and the derivative of the product. Okay. So I know that if I zoom in at the curve for f, I will see this stand double. And if I zoom in at the curve of g, I will see this stand double of g. Why do I say stand double? Is because look at it. Instead of multiplying f times g, I multiply their stand doubles. You see, they're very similar, right? So in other words, this guy is very similar to f, this guy is very similar to g. So multiplying f times g is similar to multiplying those guys together. And when I multiply those together, I'm hoping that I will see what sort of slope am I getting. What sort of line and what sort of slope of that line am I getting? You understand? My question is this: if I zoom in at f times g, what slope of the tangent line do I see? So f times g, I hope I will see a straight line. And then my question is, what's the slope of that line that I will notice? So it's very imaginative that we do here. Okay, guys? I will show you another way of doing that, but that other way is less imaginative. This is pretty interesting that you just have to picture quite a few things together. So then when I carry out this multiplication, take this parenthesis times this parenthesis, I get f times g, which is here. I get f prime dx times ga, and then I get f times g prime dx, and I can factor out dx, and I have this expression. And finally, I have this expression multiplied by this expression, which is f prime g prime dx squared. Do you get it, guys? It's just a regular foiling. In other words, what I do is nothing more than this times this, this times this, this times this, and this times, yeah, sorry, what is it? This times this, and this times this, right? That's all I'm doing. And then that's just basic algebra. Foil, yes, just foil, nothing else. Good? Alisa, you look sad. Do you understand it or just no, not at all? Clear, guys? Clear, Alisa? Yes, or any questions? And Yufu, is it clear to Yufu? Well, you see, that's what you practice thinking about it, guys, and the strategy becomes very apparent to you. Okay, you try to internalize this. I hope that's what you're trying to do, is to internalize those concepts so that you can figure out formulas that nobody ever showed you. Then that's a great achievement. Okay, just you figure out new formulas without me showing you how to figure something. You actually come up with your formulas. So it's very so. Yeah, so we'll talk about that again even more, but so this is what we get, guys. You see, this is what we get. Can you now look at this expression? Can you see what's the linear part of that expression? What would it look like if dx, x is then very close to a, right? So what would it look like? You understand what is dx? Dx is very small. It's like in this picture here, guys. You see, this is your dx. This is your dx. So if dx is very small, that means that the distance between the left and the right wall, that's your horizon, is very small. But if I zoom in, look at it. When I zoom in, I make this wall the left edge of my screen, this wall the right edge of my screen. My entire screen is just this piece. It looks like a line segment. You understand? That's what I mean. That's how I understood that if I zoom in at the curve, I will see a straight line. Remember the discussion? So this is a bit abstract. I don't want to see the graph, but I say, well, this function is differentiable. When I zoom in, I see this line. And when I zoom in at this graph, I see this line. What line will I see if I zoom in at f times g? That's the question I'm asking. Yes? So then you realize, okay, the stand doubles can be used to multiply against each other instead of f multiplied by g. And then when I FOIL, I see this expression, guys. Right? So this is up to degree 1. So this is degree 0, degree 1, and this is quadratic. Yes? So now let's imagine. Now it's especially tough now, guys. Right? So what will happen if x is within 10 to the minus 6 meters away from a? That means it's a micron. If you remember biology, what is a micron? It's extremely small. It's a millionth of a meter, and you cannot see a micron with your naked eye. Correct? So imagine that I have x is at a distance of a micron from the point A. Okay. So and then I carry out a magnification of 1 million times, and I look through a very powerful microscope that multiplies the micron by 1 million times. The micron will look to me like what's the length of the micron now under the magnification? You understand? 1 million times. Can you tell me? So here the micron is invisible. I put goggles that magnify the micron to be a million times larger by a factor of a million. How large will the micron appear? Careful for close, but much bigger than 1 millimeter. My 1 micron is 1 millionth of a meter, and I magnify it by a million. How large will I see the micron? Yes, of course. 1 meter, Brandon, that's right. You understand what's happening? When I'm zooming in on the curve, what am I truly doing, right? Look at it. Can you imagine zooming in, right? So here is a tiny interval. What happens when you zoom in? You see? Even though I don't move my fingers because I move them closer to the camera, the edges of my fingers, they start to split apart until you don't see them anymore, right? Until the screen is, look at it. You see what I'm saying? That's zooming in, right? Zooming in makes the same distance appear much larger, correct? So imagine that that x is when this limit is within 1 million units away from the point A. So if I zoom in by a million times, how wide will the distance between the left and the right wall appear? You see? Dx is this thing, yes? Dx is this thing. How large will that distance appear? 1 meter. because 1 millionth of a meter multiplied a million times is exactly 1 meter. It's pretty big. I cannot show you a meter. This is not a meter. Meter is bigger, right? Good. Now, could you tell me what about dx squared? How large will that appear under magnification of 1 million? So again, dx is 1 millionth of a meter. What would be the size of dx if I multiply the micron a million times? What would that be? Would you see this? You see, you understand this idea, guys? What is it that you're doing when you're zooming in on a curve, right? What you do is you look at a strip, right? So near x, when you zoom in on a curve, you imagine you zoom in here, let's say. You see this, guys? This is where x is particularly at a particular distance from 9, right? Let's say this distance is maybe 1 unit. So x in anywhere in this blue region, it's within 1 unit away from 9. Let's say this is this distance, right? What will happen? And then you look at the strip only where you see the curve. You see? So let's say the tip of my fingers is where you see the curve. What happens when I begin zooming in? It's like I'm getting closer to it, right? You see, from a distance, my horizon is wider. I can see the left edge and the right edge and beyond it. But as I zoom in, do you see what happened? Don't you ever do that, guys? Right? My finger is getting bigger. You know this experiment, right? If your face is the size of your palm, then you're a moron, right? Right? That's what happens. Same thing here. Well, at least one person is laughing. Others are too tired to think about it, right? Do you understand what I'm saying? So you're zooming in at this interval, and the interval now becomes your full screen. Your horizon is much narrower because you're zooming in, and then you see this slide segment. So I'm asking this, right? So zoom in such a way that the 1 micrometer appears to you to be 1 meter in length. You zoomed in by a million times. You know, the length now appears to you 1 million times what it is.
Wait,
so when it appeared to you as a micron, now it appears to you as a meter. So you're saying what I'm talking about. It's not even about the math. I'm trying to cause your graphics processor to start generating images, right? It's beautiful image, right? When you see something like you're in space. If you're blind, how beautiful is it? It's not interesting, right? You don't see anything.
Wait, so are you trying to say is that I know what you're trying to say. It just looks, so I'm basically getting the two lines, right? I'm getting the straight line. Also, I'm using basically the tangent line and the curved line, right? With those two lines, right? I'm basically using this formula, right? And finding the basically the accuracy of those two lines, or finding the straight line in between those lines, if I'm wording it right.
Wording is it's a complicated thing there. Okay, so let me try to get see what you were talking about. So again, right? So there is this idea of zooming in. The first concept is take a differentiable curve. Forget about the product rule. Take a differentiable curve. Zoom in at that curve.
Okay.
You will see a straight line. How do I know? Because when you zoom in, your x horizon, this strip will be very narrow. You understand?
Okay.
That x is within, let's say in this case, within 9. And if x is close to 9, that's just the definition of the derivative. So calculate the slope between this point and that point. Or between any point that you see here in your horizon. This is your horizon. When you zoom in, this wall becomes your right wall, this wall becomes your left wall. So you don't see them, right? That's your horizon. Take any point x. Let's say this is the point x, that's your f of x. Calculate the slope. You'll get some number, calculate the slope using a different point. You get some other number, but the numbers start looking the same. Because you remember, if we assume the function is differentiable, we assume that the derivative limit will exist. This type of
Okay.
limit will exist, right? We see
So
z going to x. What is z going to x? Well, this is 9 is your x, and z is here. Z going to x means that z cannot move very far from this point, and that means that my horizon is actually very narrow. Okay, so that's how I know that having the slope for formula work will means that I will see a straight line. Do you understand, guys, how I visualize it?
I get it. Okay.
And the rest of you, right? So some of you look and I think, no, I have no idea, and I give up, right? So, so no, guys, you understand it? Mr. Bain, do you understand it? Christian, I mean, right? Is it what you call him from Batman? Right, right. What is it? What is it that you call this guy? Bane. Yes, I was right. Okay. Good. Are we with me, guys? Are we all together? Do you remember? This is kind of very simple concept. Zoom in at the curve, you see a straight line. Why? Because if you could calculate the derivative, that's what it means. Calculating the derivative, you have this. Remember this bouquet of lines that we talked about. Okay, so that means what? That means that, so that's what I want you to have in geometry concept, right? Is that a curve that's differentiable looks locally like a straight line. And the slope of that straight line will be the derivative. Good? So then this is a bit more abstract, right? What can I do with that information? I can carry out the local calculation. Instead of multiplying f by g, I multiply the equation of one line by the equation of the other. Okay? I have those two equations because you see this is locally it looks the same. This function is not very distinguishable from this line where x is very close to a. Okay, so I expect the product to be essentially the same whether I multiply the actual functions or their stand doubles. And when I multiply their stand doubles, then I see this dx. So it's a difficult idea, guys. I understand. I mean, right? Difficult idea. I'm just trying to engage your graphic card. I'm hoping it improves from that. Okay. So what happens now? Dx is 1 micrometer inside. If you multiply it a million times, in other words, you zoomed in so that it looks to you like 1 meter. How large will dx squared appear to you? Will you notice dx squared? Well, you will notice dx squared. So how large is dx squared if dx is now appearing to be 1 meter? Dx squared will be what? It will appear to be what? Come on, you can do it. 2 meters? Dx squared will be 2 meters? 1 meter? Let's look at it. 10 to the minus 6. So dx squared will be 10 to the minus 12. When you square it, it's invisible. It looks like a micrometer under a million zoom. You see, zoom a million times and it will be a micrometer. Can you imagine the scale? You don't see it. You understand? Under a million zoom, it's tiny. It's like, you see, 1 meter is huge, right? So you understand, micrometer is tiny. And this dx squared is so tiny compared to that tininess that you will not even see it, even if the micrometer is made a million times bigger. If it's made a meter, I cannot spread my arms wide enough for you to see a meter. Under that scale, you will not see dx squared. And you see, you understand what I'm trying to tell you? So that when you are zooming in, yeah, if you know it's smaller, right? When I'm zooming in, this dx squared, this part is invisible. Do you understand why? Because it's a square of a tiny number. This part will be invisible. It would look like a straight line. So roughly the philosophy is this, guys. When you zoom in on a curve that's differentiable several times, from some distance it starts looking to you like a quadratic. From a bigger distance it might look to you like a cubic, but as you are zooming in more and more and more, it eventually looks like a straight line. You understand? The complexity of the curve decreases as you're zooming in at the curve. So let's say from a big distance, it might be appearing to be a polynomial of high degree. Zooming closer, the higher degrees become irrelevant. So eventually, all you are seeing under far enough zoom is just a straight line. Okay? So Are your minds are blown, overcooked, overclocked mechanism? So dx is 10 to the minus 6. I just picked it to be 10 to the minus 6. Yes, I mean, I could make it smaller. The point is, I'm trying to explain to you how, without seeing the graph, I can imagine that it would look like a straight line. And so it would look like this part, guys. You see, only the first part is, if I can barely see, let's say, dx, even under high zoom, then this part is all I see. And that's the equation of a line, because dx is x minus a, okay? So this is what I'm saying. So this is the y coordinate, and that is the slope. Do you see? The point here is that using this idea, I can right away figure out what would be the slope of the derivative. Here it is. Yes? It's the derivative at a times ga plus fa times derivative of g. So the other way to do it is by definition. Let's actually carry out one calculation, because I'm not sure if you are completely fried. Okay, so this is the idea how you calculate the derivative, guys. Okay, so if you have a product, that's what we just hopefully verified. I will verify it using the definition in a moment, but let's first actually carry out a calculation here. So if I have a product of f times g, the derivative is just the derivative of f times g plus f derivative of g. In other words, you can imagine the derivative travels from first function to the second function. Here it's on the first function, plus it traveled to the next function. Do you understand? Now, let's see, without any further explanation, could you, using this formula, I will still keep it written here, could you tell me what's the derivative of x squared times e to the x?
You said we plug in what?
Well, here is the formula of a product of two functions. If I know how to differentiate the function f and how to differentiate the function g, then the derivative is the derivative of first times the second function without touching it, plus the first function derivative of the second function. So the derivative travels. You can imagine it's like a traveling salesman. It's from one function to the next. And then there is a plus in between its journeys. Wonderful, Rafid. Very good. Graphics, guys, right? Install a better graphic card here. Okay, so yeah, it's Muhammad, correct your solution, just write it again, just to, I'll see what you are saying. You mean e to the x full, correct? Not 2x e squared, you mean e to the x. All right, cool. Very good, very good. So you can carry out this calculation, guys. Make sure you can. But the calculation is secondary, I think, right? I just want you to see why the formula is true. So again, this is what we have. We can label the first function as f and the second as g. And then we have this traveling salesman. It's the derivative of f, the derivative of g. Yes? Derivative of f is just I take the derivative of x squared separately. It's 2x e to the x. And here I take the derivative of e to the x, which happens to not care when you take derivative. It's the same thing. Good? Okay, let's do one more question. I will just write it. So please take the derivative. Again, we have very few interesting functions here, so let's do it like this. So let's have 3 minus 7x plus x cubed, and I multiply it by e to the x. Take the derivative of that expression, please. You can do it fast. Okay, let's see. Yes, Rachel, and many of you, you forgot to put parentheses. Right, so even if you had the right idea, your parentheses make it otherwise. All right, let's solve it together. So again, we can make this first function f, second function g, right? So what we have is a derivative of f times g is the first thing I write. So that would be derivative of f is minus 7 plus 3x squared. And then I don't bother with the second function, with g. Then I write plus. I don't bother with the first function. I keep it as it used to be. So 3 minus 7x plus x cubed multiplied by the derivative of e to the x, which ends up being still the same thing. So that's here simply f times g prime that I have. Good? Okay. Let's return to the text. So before I move on, guys, let me see the geometric idea. How many of you understood what I did there? You understand how I was able to figure out the derivative geometrically, that's the formula? Let me know honestly. It might, maybe on first trial, it's a bit difficult. I have other ways of explaining it. So you know how you understand it truly if you can, at home, you can figure out the derivative by yourself. Actually, for quotient rule, I will ask you to figure it out using geometric idea. Just figure out the formula using geometry. We can even practice it together if you're interested, right? So seeing formulas that you never saw before, hopefully. So this type of idea, especially when I'm hoping some of you will go through complex analysis, and this is pretty a good way to understand what's happening. This geometric way is a better way to figure out what is the derivative of a complex function, for example. Okay, so for calculus 1, you can get away with other ideas. Here is the other idea, guys, right? So we can just go ahead when we don't know something, we can apply the definition. The derivative of f times g is the limit as z goes to x of this function evaluated at z minus this function evaluated at x divided by z minus x. Yes, so we are going to do it this way. Now, what am I searching for within this expression? I am assuming that f has a derivative, so I'm searching for expressions of this form because I can then compress it and say f prime of x. And expressions of that form I can compress and say g prime of x. So within this formula, I'm searching for the definition of derivative for f and for g. Good? Write in the comments if you are still here, guys. Understand? Yes? You see, basically, why is it you need, so that you need to not be blind. What is it that you are searching for? If you can answer that, you can find it. So notice when in many things, when you talk about it, right, you cannot say very clearly what is it that you want, what is it that you're searching for. And that's why it's hard to find it, because you don't say clearly what is it that you are interested in. So here is what we might try to do. Look at it, guys, right? So we have z together and we have x together, but we don't have mixed x and z. So that's what I introduce. So I subtract f of x, g of z. Why do I do that? Because look at it here. I would be very glad to factor out g, and then I'll have f of z. Look at it, at this expression. Let me try to write, maybe that helps. So look at it, guys. I think of it and I say, oh, I'm not very happy with this expression. What if it were f of z, g of z, g of x, let's say. Minus f of x, g of x, yes? Then I will be able to simply factor out g of x. But here we have g of z, g of x. They're not the same. There is a mixed term that we need. So then I introduce this mixed term. You see, if I introduce this part, I can factor out g of z. And then because I introduced it, I have to, if I subtracted f of x times g of z, I have to add f of x times g of z. And here, I can factor out f of x. Yes? With me, guys? You see how I break it apart? Like this, look at it. So this part over z minus x, and this part. So this part goes here, this part goes here. And then we have a fraction. So it's the left circle divided by z minus x plus the right circle divided by z minus x. And then I can factor out g of z in this case, and I can factor out f in this case. Clear? Okay. So we are, oh, look at it. And when I factor it, I recognize the derivative of f. This is the derivative of f. And here is the derivative of g. So then some limits are very easy. Z going to x, this f of x is unaffected. This limit by assumption, by hypothesis, is derivative at x. This limit by hypothesis is the derivative of f. You see this line? The only possible thing, you might have actually not noticed it. How can I guarantee this? Why is the limit as z goes to x of g of z equal to g of x?
Because Z is getting closer and closer to X, so that's what you plug in.
That's very tempting, but be careful, right? We remember that limits are not the same as plugging in, yes? And thank you, Karolinushka, for speaking. You have to be very careful, guys, right? It's very tempting. You see, Z is almost X. So you would say, oh, this is essentially X. But what you're saying is that G is eating creatures that look like X. Why do you think that the digestive system responds in the same way as if it just eats X? That's the question.
Because they're very similar.
Well, let me
or they're close.
Let me show you this function. Again, there are not many interesting functions. Can you see the whiteboard or not really? I'm sharing the whiteboard, yes? Yes, okay, so what about this function? Suppose that my g of x looked like this. So it were equal to, let's say, g of z. Let me just make it so that we don't have to speak about it. So g of z looked like, let's say, z squared if z is not equal to x, and it looked like 5 if z equals x. To be precise, maybe let's say this. I'm worried that it will. Just a second. Let me make it just numeric. So we have g of z equal to z squared if z is not equal to 1, and it is equal to 5 if z is equal to 1. So then my x that I will select, x is equal to 1 here. So tell me, what is g of x? That's the same as g of 1, right? Which is what? What is g of 1?
5.
5. What about limit as z goes to x of g of z? What is that? That will be, z is 1 here, right? So so that would be limit as z goes to 1 of g of z, which is limit as z goes to 1 of z squared, which is what? Which is 1. Yes? That's what I'm trying to say, guys. Yes? So how do I know that such a thing does? Look at it. Plugging in 1, when g digests 1, it produces 5. When g digests numbers close to 1, it produces outputs that are close to 1. Right? Not the same. So how do I know? How do I know that will not happen in here? The function g, let me remind you, by assumption, this limit exists, which means the function is differentiable. And that means what? If a function is differentiable, then it is what? Do you remember the Megalodon tooth?
So are you saying that it's because we were doing what we did before, where we're replacing with the linear approximation?
Yes, or in essence, that's what we know intuitively, is that locally it looks like a line, and line is in particular continuous. It's one whole piece of material, so that doesn't happen. Over there, we have a tearing in the fabric of the curve. Right here, it's continuity. You understand? So the reason we know that this to be true, it's very easy to miss, but that's because of continuity. And intuitively, differentiable means you see a straight line segment. And if you see a straight line segment, that means the function is a whole, right? Locally, it's one whole piece. And we proved it again. Remember that, guys? You see it intuitively. You also want to prove it formally. Wonderful. let's continue. Are you holding up? Alisa, how are you? Ах, Alisa. You know the song Ах, Alisa, как же нам встретиться? Do you speak Russian, yes? So you might know that song, no? I should play you that song, maybe it will cheer you up. So stay after class, I will play you the song about Alisa. Everybody, right? You see, I know a song about everyone. I'm sure I must know a song about Carolina, right? Okay, guys. Hold on, we're climbing the mountain, right? We're exhausted. There is not a lot of oxygen. I want to. There is not a lot of oxygen, but we are climbing up the summit. So here is the question that I want to ask you guys. Let's see if you can come up or imagine what the formula would be like if I have f, g, and k, three functions, and I multiply them, and I want to find the derivative of the triple product in terms of the individual products of those functions. Can you figure out, can you guess perhaps what might be the formula? It's essentially, I wonder if you could guess. Right, the formula, let me try to tell you what I mean, guys. Right, so if I have f times g, the formula is f prime g plus f g prime, yes? That's the formula for the derivative of a product. Now, what do you think is the formula if I have f, g, and k derivative? What would that be if you have three functions there? Can you figure it out?
Wouldn't it equal it's almost it wouldn't it equal f derivative of f, oh never mind, never mind.
Think about it, guys, you can do it. Okay, so it will be ready. Okay, two people have it. Okay, great. Christian, you got it. And Rachel, wonderful, ditto. So yes, you have a sense for this pattern. And that pattern is true. Okay, so this is going to be the formula, guys, right? The derivative is going to travel through all the functions. First, second, and third. Make sense? Very easy to remember this pattern. And in fact, if you know the product rule for two functions, it's easy to verify for three or more. Because the derivative of three functions, it's like I can group together two functions. And now I have the square bracket function times k. So the derivative is the product rule of those two functions. Derivative of first function second plus first function derivative of the next. And then I do the derivative of f times g, expand it, and simplify. And I get this pattern. Okay, I get this pattern. So for example, let's quickly do one question here, guys. New share. So again, we know so few functions that it's just terrible. But let's suppose we have root of x times x cubed plus 1 times the cube root of x. So this is my triple function. I want you to find the derivative of that. You can recall that This is x to the power of 1/2 x cubed plus 1, and this is x to the power of 1/3. If you prefer, you can do that. All right, guys, so let's finish it up. So because we only know how to take derivatives of functions of the form 1 over an integer or functions to the integer, right? Then I will use the triple product to find what's this derivative. So it is the derivative of x to the 1/2. It's 1/2 x to the 1/2 minus 1 times the other functions untouched plus x to the 1/2. Derivative of the middle function is 3x squared plus 1, and then the next function untouched, and then plus the first function untouched, the second function untouched, and the last function we take the derivative, it's 1/3 x to the 1/3 minus 1. Okay, so of course, let me one small thing, guys. Of course, you might have noticed that, for example, x to the 1/2 times x to the 1/3, I can combine them to be x to the 1/2 plus 1/3, and that is simply x to the power of 5, 6, right? So that's 3 plus 2 at 5, 6. And then you might, if you know this pattern, it's the derivative is 5 over 6 x to the 5 over 6 minus 1. But we haven't established that this law is true. Okay, we established only that if it's x to the power of an integer, the derivative is n x to the n minus 1. And we can also easily establish that if it's 1 over an integer, the derivative is 1 over n x to the 1 over n minus 1. But we can actually figure out eventually that if you have x to any power alpha, you will be able to use that. Its derivative is alpha x to the power of alpha minus 1, where alpha is any real number. Okay, so let's stop this lesson, and I will play Alisa's song so that she will cheer up a little bit, and maybe some of you too.